Hello, my name is Jung Kim and my major is the Department of Automotive Convergence. Let's start a paper review presentation for a Markov decision process-based collision avoidance in IoT applications. The table of contents is as follows. Recently, the unmanned aerial vehicle called drone has received a lot of attention in research and industry. It is applied in various ways in real life by many studies. One example of drone application was used for crop management. To make this application more reliable and robust, it is necessary for the system to have a long operating time. In order for IoT devices to operate for a long time, it is important to use batteries efficiently. This requires avoiding idle listening, which continues to wait for signals. As a way to avoid idle listening, there is a system consisting of low-power wake-up radio and main radio of IoT devices. Because the wake-up radio receiver can wake up the main radio can maintain the sleep mode and save energy. However, if multiple wake-up signals enter the receiver, a collision occurs. For example, when a drone is used in agriculture, multiple drones send a wake-up message to a single ground sensor node, then a collision occurs. Multiple retransmissions are required in the event of a crash. This is a waste of energy, which violates the purpose of extending the lifespan of IoT devices. This paper presents a methodology that applies the Markov decision process to prevent collisions between wake-up signals and minimize unnecessary delays. Let's take a look at the techniques used to prevent collisions on the wake-up plane. The first one is multi-channel techniques. This technology allocates different frequency channels to avoid collisions. When the transmitter transmits the packet, adjust the wake-up radio channel to match the frequency channel of the receiver. If the channel is empty, send the wake-up message, otherwise wait. However, this method does not alleviate conflicts because it can send a wake-up message to the same time slot. Next, you can use TDMA-like scheduling. This approach can prevent collisions on small networks, but not on large networks. Finally, there is a random binary backup technique. This approach is inefficient because it does not take into account the size and density of the network. Therefore, in this paper, the network was modeled using MDP and then optimized using policy iteration. Let's look at the problem of collision on the wake-up plane. Sensors on the ground are used to examine the condition of crops, and drones are used to obtain information such as images. Ground sensors store information and transmit it when a drone comes near them. Alternatively, ground sensor nodes exchange information with each other to inform urgent situations such as fires. Therefore, the transmitter of the wake-up message requesting information is either a drone or a ground sensor node, and receiver is always a ground sensor node. When multiple drones or ground sensor nodes send a wake-up message, a collision occurs and multiple retransmissions are required. However, if only one transmitter sends a wake-up message to one receiver, the receiver will receive information about the transmitter. The microcontroller turns on the main radio, and the main radio transmits the stored ground information. Next, let's look at the Markov decision process. MDP provides a mathematical framework for modeling decisions. This allows us to deal with stochastic control in discrete time. The elements of MDP are agent, environment, state, action, and reward. Agent refers to the decision maker. Environment means everything that interacts with the agent except for the agent. State means that the environment provides for a new situation after receiving the agent action. Action is decision that agents make to interact with the environment at each step. Reward is numerical value that the agent must maximize cumulatively. Now, let's look at the elements of each MDP applied in this paper. The agent is the drone or ground sensor node to which the wake-up message is sent. Action consists of TR and W. TR means sending a wake-up message in this time slot, and W means waiting without sending a wake-up message in this time slot. State consists of 5 types. Successful transmission is that only one decision maker sent a wake-up message, and the agent should try to increase the opportunity to enter this state. Collision means that multiple devices send wake-up messages at the same time. Next, there is idle in the state that the agent chooses waiting. Idle 1 is a situation in which only one of the N-1 devices is selected for transmission except for agent. Idle 2 is a situation in which several of the N-1 devices, excluding agent, have transmitted. Idle 3 is a situation in which all devices except agent select waiting. Transition probability is the probability that when an agent selects action AT in state ST, it will move on to the next state ST plus 1. The network consists of N devices, including drones and ground sensor nodes. P is the probability of packet transmission following the Poisson distribution. Let's look at the formula below. For successful transmission, N-1 devices must select W to succeed in transmission when the agent selects the action of TR. Collision is a complement of successful transmission, so subtract the above value from 1. Idle is N-1 times P times 1 minus P to N-2, because only one of the N-1 devices choose TR when the agent chooses the action of W. Idle 3 is 1 minus P to N-1, because all N-1 devices have chosen W. Idle 2 is the probability of excluding idle 1 and idle 3 when W is selected. Next is cost. Cost function CS represents the cost for a given state. The cost of successful transmission is the difference of specific constant G and the cost needed to send wake-up message. At this point, the cost E is the length of the wake-up message multiplied by the time required to transmit 1 byte and the power required to transmit it. Cost for collision has failed to send the wake-up message, so it costs -E. When idle, I didn't send the wake-up message, but it includes the cost of waiting time. I is the cost of waiting time, which is less than E. I is the length of the message multiplied by the transmission time per byte. Alpha, beta, and delta are thresholds between 0 and 1. They are used to improve network performance. The reward is the sum of costs at each state. The value is the expected return of the total discounted reward multiplied by the discount factor for each time step for a given policy. When you get the Bellman equation solution, you get the optimal policy pi star. In this paper, we used policy iteration as an algorithm to solve optimization problems. Therefore, the resulting policy is used for collision avoidance at wake-up plane. The proposed method is WUP-MDP and compared to the conventional RFID impulse. Metrics are the number of successfully transmitted packets and the gain of successful packets and collision packets. In figure 2, the number of devices N is x-axis and P is fixed to 0.03. As a result, WUP-MDP demonstrates greater success. In figure 3, the transmission's probability P was placed on the x-axis and N was fixed at 15. Experiments show many differences in gain when P is small, but if P is greater than 0.05, the gains are similar. In conclusion, this paper introduces how to deal with collisions of wireless communication networks in wake-up planes using WUP-MDP based on a Markov decision process. This demonstrated efficient policy decisions to avoid collision between wake-up messages. This result saved energy wastage from wake-up message collision. That was the presentation of a Markov decision process-based collision avoidance in IoT applications. Thank you.